Greetings. Our team is glad to present our work in ultrasonic fatigue testing under biaxial stress states. Now we're going to begin talking about the ultrasonic fatigue machine. How does it work? Its components. Then we're going to talk about the specially designed specimens, the base concept, the improved concept, and afterwards we're going to talk about the finite element analysis we have conducted around the specimen and around the setup, tested material used in this study, and its respective experimental tests, results, and final remarks and conclusions. Now, our machine follows the same concept of the basic tension compression ultrasonic fatigue machine. It follows the same booster, horn, and test specimen setup. The only difference is the pattern horn and the specially designed specimen that are able to induce torsion simultaneously. The setup is able to induce simultaneously torsion to the tension compression because the pattern horn induces a second resonant mode to the specimen. The setup is made so there is only one fatigue testing region where there is tension and torsion, and the specimen is adjustable so that we can have the tension-torsion ratio we desire. The pattern horn is the essential component that gives the ability to induce tension and torsion simultaneously. It transforms partially the actual displacement that comes from the piezoelectric transducer and the booster to a combination of rotation and actual displacements that are induced to the specimen. Now, from the horn-induced displacement combination, the actual and the rotational displacement, the specimen is simultaneously excited in two resonant modes. To have a rotational resonant mode and a longitudinal resonant mode at the working frequency, the specimen was specially designed with three throats, two secondary throats at the edges and one main throat at the center. Now the specimen having this geometry will have the first longitudinal mode for tension stresses. This is very similar to the tension compression ultrasonic specimen, and the third rotational mode where each cylindrical section will rotate in a different direction, thus inducing shear stress in all three throats, and the combination of these two modes create tension and torsion in the main throat. Here we have a small animation of the two modes to better understand how the specimen is behaving. On the left we have the longitudinal mode. This is very similar to the ultrasonic specimen tension compression behavior. On the right we have the rotational mode, where we can clearly see that each cylindrical section rotates at a different direction, thus creating torsion in each throat. Now, after several iterations of the specimen geometry, we reach this simpler and more consistent specimen geometry and respective variables, the A, B, C, and R, and through manipulating these variables, we can thus achieve the desired tension and actual stress relation. Now, we use finite element analysis. This is the final result of one specimen in the booster horn specimen set. We manufacture three different specimen geometries in this work, but only two are presented in this. Maybe I can change this. Now we're going to make a comparison through finite element analysis of the first and the new specimen geometry. Now the first specimen geometry follows certain rules. These rules resulted in the equal shear stress between all three throats, and this was the result of a similar rotation between each cylindrical section. Now, by manipulating the geometry, we were able to increase rotation between cylindrical sections, and thus we can achieve a higher shear amplitude in the main throat that can be manipulated and can be changed to our desire. Looking at the first tested specimen geometry, we have an equal rotation between cylindrical sections, which leads to an equal shear stress amplitude between throats, and the difference is that makes the stress combination higher in the main throat is the actual stress, where it's much higher in the main throat. Now, looking at the new geometry, we're able to increase the rotation. We can clearly see the rotation is much higher in the cylindrical sections between the main throat, which leads to a higher shear stress in the main throat, and therefore the combination is higher in the main throat, not just because of the actual stress but also in the shear stress. This increase in rotation, this manipulation of rotation, creates the ability to change the relation between the torsion and the tension. In this study, we have used ACP20 steel to manufacture all specimens. We conducted several basic mechanical tests to determine basic priorities of the steel, and through them we have designed specimen 1 and specimen 2, which have different shear and actual stress ratios. Now, in ultrasonic fatigue, the high stress region will have a higher and considerably heat generation. So the first tests conducted was through a thermal camera, proved that indeed we have the highest stress combination in the main throat by having the highest heat generation in the main throat. This can be seen in two different specimens being tested on the image. Now, to better understand and make a complete analysis of the behavior of the specimen, two different lasers were used to measure rotational displacement and actual displacement, and a rosette strain gauge was applied in the main throat of the specimen. Through analysis of the measured displacements and measured strains, we can clearly see a linear relation between the actual stress and the actual displacements, just as in tension, compression, ultrasonic fatigue specimens. Now, the same cannot be said in the shear and rotation, since we are not measuring at the highest rotation point, and also we observed different shear stress amplitudes between the same specimen geometries. Looking at one example of the strains obtained for one of each geometry, the highest shear specimen we have obtained for one a 0.5 ratio, while the specimen we have a 0.38 ratio. Testing these specimens, we have achieved a fatigue fracture in the main throat. Then these specimens, after propagating a certain length of fatigue fracture, they lost resonance and they needed to be split up in another machine. Now, looking at the 0.38 lower shear strain specimen, we obtain a 20-degree angle for the point of initiation, where it is located at the surface, right around here. Comparing now to a higher shear specimen, is still on the surface right here on the point where the point of initiation occurred, but we obtained higher angle of initiation, and we also can see marks which are associated with torsion fatigue. Now, the taken conclusions of this work. We tested two different geometries in tension and torsion. These geometries had different stress ratios. Through the behavior analysis of the specimens, we have proven a linear stress displacement relation very similar to the one observed in ultrasonic tension compression methods. Through the analysis of the fatigue fracture, we have seen that crack initiation angle and the characteristics of the fatigue fracture surface are dependent on the stress ratio and the stress intensity applied. Now, the higher the shear and actual ratio is, torsion fatigue marks appear and the crack initiation angle is higher. On behalf of our team, we'd like to thank you for all your attention.